Hello, I'm Seema and welcome to part 9 of the chapter Chemical Bonding and Molecular Structure. In the previous parts, we have been discussing some bond parameters. We discussed bond length, bond angle, bond enthalpy, bond order, resonance structures, and now we are going to discuss the polarity of bonds. Do you know that no bond is, when we talk of bonds, we call them covalent bonds or ionic bonds. And no bond is, a covalent bond is not completely covalent. Every covalent bond has a certain amount of ionic character to it. Similarly, an ionic bond has some amount of covalent character to it. So it's not like a bond is totally covalent or a bond is totally ionic. You may define bonds as covalent bonds based on the sharing of electrons. If they share a pair of electrons, the bond is called a covalent bond. But if there's a complete transfer of electron from one atom to the other, and the ions that are formed, the ions stay together because of electrostatic forces of attraction or Coulombic forces, that kind of a bond, we call it an electrovalent bond. But all covalent bonds have some degree of ionic character to them, and the ionic bonds, they have some degree of covalent character to them. Now we are going to discuss about the ionic character in a covalent bond. When we say bond, we mean it is a covalent bond. And when we say polarity, a covalent bond is not supposed to have polarity because it is formed by the sharing of a pair of electrons. There are two elements or two atoms which are electronegative, that is, they needed electrons to complete their octet, and they shared those electrons with a neighboring atom which also needed electrons to complete their octet. And when they share the number of pairs which were required to complete their octet, they form covalent bonds. So you would expect, now for example, what are the type of covalent molecules that you see? If they were diatomic, you would imagine molecules to be homonuclear. Homonuclear means the ones which have the same nucleus, and we know the atoms which have the same nucleus or the same number of protons and neutrons are atoms of the same element. So when you have homonuclear molecules, for example, two atoms of hydrogen are combining together to form a molecule of hydrogen, two atoms of chlorine are combining to form a molecule of chlorine, O2, N2, these are examples of molecules that are homonuclear. What would you expect when a covalent bond is formed? Let's take the example of hydrogen. Both the hydrogens have one electron each, and in order to complete their duplet, they share this one electron with the other hydrogen. Thus, both the hydrogens have their duplet completed, and the shared pair of electrons falls between them. We understood this and we drew this in Lewis structures, that the shared pair of electrons come in between, and the two atoms, they share this pair of electrons evenly. So both the hydrogens have the same deficiency, they have the same nucleus, they are identical in everything, therefore their electronegativities are also the same, and hence the shared pair of electrons should be shared equally by the two atoms. If the electrons should be shared equally by the two atoms, you would expect this to be totally covalent. There should be no ionic character, there should be no polarity. When we say polarity, poles means the positive and negative charges, and they are centered at different places, then we say the molecule is polar. If a molecule has positive and negative charge separation, they are not mingled, and you can tell, okay, this part is positive and this part is negative. That kind of a molecule is a polar molecule. But in such homonuclear molecules, we do not see any polarity, we do not see a difference in the positive and negative charge, and the electrons seem to be equally shared by the two atoms. Actually, no two atoms, even if they are identical, are absolutely non-polar. You know, it's hard to believe that even these, where you would expect these molecules to be, but for all practical purposes, we call them, these are non-polar molecules, we treat them as non-polar molecules, they are very much non-polar molecules. But how do we say that every covalent bond has some amount of ionic character. On what basis do we say it for such molecules? I'll just explain. When we talk of the quantum mechanical model of an atom, we say that electrons are constantly moving and they are not static. Although we assume that this pair of electrons is being shared equally by the two hydrogen atoms, at any fraction of a second, there is a possibility that these two electrons just move a little bit more towards this hydrogen, or in a certain moment, these two electrons may move slightly towards the other hydrogen. When these two electrons move towards this hydrogen for a fraction of a second, for that fraction of a second, this side of the molecule acquires a partial negative charge. And simultaneously, this part of this hydrogen becomes partially positively charged because the electron has moved slightly away from it, and therefore it's the positive charge which becomes more prominent here. So for a fraction of a second, even if it's just for a fraction of a second, the molecule did acquire a partial ionic character. So although since it's only for a fraction of a second and we hardly ever notice it, predominantly it is nonpolar, such homonuclear molecules are known as nonpolar molecules. If you come to heteronuclear molecules, when we say heteronuclear, it means the molecules which have more than one element in it, more than one type of atoms in it. Then we start observing this character, this polarity even more. And let us now see what causes this polarity. We take this example of a diatomic molecule of the type AB, where A is an atom of one element and B is an atom of another element. So if the molecule is of the AB kind, for example, you have HF, hydrogen fluoride. Out of these two elements, fluorine is very electronegative and hydrogen is electropositive. In comparison, fluorine is more electronegative. Electronegativity means that it has a tendency to pull the shared pair of electrons towards itself. It has a stronger ability to pull the electrons towards itself. And hydrogen does not have that much of an energy to pull the electrons towards itself. So this shared pair of electrons would shift slightly towards fluorine, as a result of which the hydrogen would be partially positive and the fluorine would acquire a partial negative charge. Thus, polarity is created in the molecule. Although the molecule is covalently bound, it is a polar molecule on the whole. And this polarity is, if you measure it, it is known as the dipole moment. The measure of this polarity is called the dipole moment, and it is represented by this Greek alphabet mu, mu, and it is written like this. So mu represents the dipole moment which has been created in a molecule as a result of a difference in their electronegativities, and the more electronegative element pulls the electrons towards itself. So dipole moment structurally in a molecule is represented by an arrow which is pointing towards the more electronegative element or the atom, and the tail of the arrow is towards the electropositive atom, and this cross you could use to remember that where you put the tail and the plus, this is a plus sign if you think this is the positive atom and this is the negative atom. The arrow always points towards the more electronegative atom. And why do we do that? Because dipole moment may have a magnitude. It may have a measure. The dipole moment has a measure, or this much of charge difference is there between these two atoms. But it is directional. It has got a direction, and the direction is, we take it as the direction we follow the electrons. So if the electrons are moving towards fluorine, we follow that direction of that force is towards fluorine. So it is fluorine which is causing the dipole moment. It is attracting the electrons towards itself. So we say mu is the dipole moment, and mathematically the measure of mu is the charge difference between the two atoms into the radius, that is the distance of separation between the two atoms. So the magnitude of dipole moment is measured by charge into the distance of separation. Now, in your syllabus, that is in 11th and 12th, we are not really concerned about the mathematical part of this, but just the magnitude of dipole moment and the conceptual dealing of this topic is what would be your concern. So although I will be mentioning the dipole moment from time to time to compare the different dipole moments, we are not really going into this calculation. So let us now come, the dipole moment, the unit for dipole moment is known as a debye. And 1 debye is equal to 3.33564 into 10 to the power minus 30 coulomb meters. Coulombs is for charge and meters, these are the MKS units. And coulomb is for charge and meter is for distance of separation. Now we say that dipole moment is a vector quantity. And it is a vector quantity because it not only has magnitude, it also has a specific direction. And when you have vector quantities, then the sum of such quantities does not depend only on the magnitude. It's not only the sum of the this is the dipole moment of this bond, this is the dipole moment of this bond, and the sum of these should be this. It's not just a mathematical sum of the quantities. You also have to keep the direction of that dipole moment, that magnitude in mind, and that affects the resultant dipole moment. See, I'll just come to that as we go further with this topic. So let us now, I just explained to you that the dipole moment is a vector quantity. In addition to a magnitude, it also has direction. So now we take such diatomic molecules, the AB type, different ones, and we compare their dipole moments. Now I just showed you HF. HF molecule has a dipole moment of 1.78 debye. Fluorine, if you remember from your study of the periodic classification of elements, is the most electronegative element. And hydrogen among the non-metals is the most electropositive. So the difference between their charges would be the highest. So you could say HF is the molecule which has perhaps the highest dipole moment that could be in the entire period for diatomic molecules. So the HF molecule has a net dipole moment of 1.78 debye. HCl, chlorine is, now all of them have hydrogen, so we are not taking this side, it is the electronegativity of these halogens that will cause the difference in the dipole moments. Now chlorine, HCl would have a dipole moment of 1.07 because chlorine is less electronegative than fluorine, bromine is even lesser, and iodine is the least electronegative, and that is what we observe in the dipole moments too. As the difference in the charges or the electronegativities is more, the higher is the dipole moment. And as the difference in electronegativities gets lesser and lesser, the dipole moment goes on decreasing. Looking at this, if I asked you what is the dipole moment of homonuclear molecules? Since both of them have the same electronegativity, the charge is 0 and radius, whatever it may be, the dipole moment would come out to be 0. Therefore, non-polar molecules always have a dipole moment of 0. Now you could have a polarity or a dipole in one particular bond, but there could be another bond present which is counteracting it, and although there are polar bonds, they may nullify each other's effect because dipole moment is a vector. If you have two dipoles in opposite directions, then each would cancel out each other. And in that case, the molecule, although it had bond dipoles, the net dipole moment of the molecule would come out to be 0. So what do you understand from this? When you have molecules which have more than 2 atoms, then the dipole moment, the vector sum of the dipole moments, although there may be dipole moments, the vector sum of them gives you a net dipole moment, and that net dipole moment could also be 0. So although individual bonds have some dipole, the molecule on the whole could be non-polar. So some molecules, although they seem to have dipoles, yet the molecule on the whole is non-polar. It's very interesting, but let us move stepwise. Now we come to polyatomic molecules. Instead of diatomic, we come to polyatomic molecules. One more thing, dipole moment gives you an indication of the structure of a molecule. It also gives you, if you know the dipole moment, the magnitude of the dipole moment, you would get an idea of the structure of the molecule too. And I'll explain that to you as we move on. We came to diatomic molecules. So what would the shape of a diatomic molecule be? The shape of a diatomic molecule, when there are two dots and you're joining the two dots, what would the shape of that thing be? It's always linear, it's a line. So diatomic molecules are always linear, right? And they are linear, and if you have polyatomic molecules, that is triatomic, we first come to triatomic molecules. Triatomic molecules could be of the type AB2. And AB2 type of molecules, here you may have individual dipoles, bond dipoles, but they might show an enhanced dipole or a reduced dipole. Let us see. The example of carbon dioxide. Carbon, this is the structure of carbon dioxide here, C bonding to two oxygens by double bonds. Now oxygen is more electronegative, and the electronegativity difference between carbon and oxygen, therefore the magnitude of the electronegativity difference or the charge is the same. If the magnitude of the charge is the same, what is the direction of this moment? We find that when we draw the arrowhead, that is the negative charge, or the electrons shift towards the more electronegative atom. So in carbon dioxide, the two electrons, they move towards oxygen. And here also these electrons, they shift towards oxygen. So what happens? The dipole moment, if you see, is actually pointing in two different directions and two absolutely opposite directions. Right? When this happens, this dipole, since it's a vector quantity and they are equal magnitudes, you can imagine there are two people playing a tug of war and both of them have the same energy and both of them are pulling the rope from the two sides. What will happen? Who would win? Nobody would. And what will be the net result? What will happen to, let us say you tied or something in the center to see where it is shifting. If both of them have the same energy, that marker that you put remains where it is, because none has a greater energy to pull the electrons or the charge towards itself. So, although there was bond dipole in carbon dioxide, both the individual bonds had dipoles, the net dipole moment of carbon dioxide, mu, is 0. It is a non-polar molecule. Now, if we take another example like BeF2, what do we observe? In BeF2 again, the similar situation arises. Fluorine is more electronegative. Fluorine being more electronegative, again the dipole moments are towards the fluorines and the magnitude is the same because both the fluorines, the difference between electronegativity is the same. Therefore, again, we have a similar situation to carbon dioxide and the net dipole moment of BeF2 would also be 0. So what do we notice in triatomic molecules? In triatomic molecules, or if they are linear, their net dipole moment turns out to be 0. Because if a molecule is linear, then whatever be, if let us say the charges were moving towards this, which usually doesn't happen. When we did the Lewis structures, we noticed the electropositive element usually forms the center and the electronegative ones, they form the terminals. So we find that they usually cancel out each other, but even if they were, let us assume just hypothetically that they were in the same direction, even then their directions would be opposite, and even if the magnitudes were the same, they would cancel out each other and the net dipole moment would be 0. So for triatomic molecules, if the dipole moment comes out to be 0, then it becomes clear to us that the molecule must be linear. Now let us come to another molecule, which is again the AB2 type, that is a water molecule. When we see water molecule and we know about the electronegativities, oxygen is the central atom, the two hydrogens are on the two ends, and why, although hydrogen is electropositive, it has to be terminal because hydrogen can make only one bond and cannot behave as a central atom. So when oxygen is more electronegative, we find that both the hydrogens should allow their dipoles should move towards oxygen and their magnitudes should be the same. So if water molecule was linear, the net dipole moment of water should have been 0. But we find that the dipole moment of water is 1.85 dBi, which is pretty high. So what causes this dipole in the dipole moment in water? You can explain that by thinking that the water molecule may not be linear, it may be an angular molecule. The two hydrogens are like this and the water molecule is angular, and what happens as a result of its being angular? Now these two dipoles, they are shifting the electrons towards oxygen. So if you really see, it seems to there's a net motion in this direction. The motion of electrons, if you take hydrogens here and oxygen here, the net movement, although it is like this, is actually from hydrogen to oxygen. So you see the net dipole is in this direction. So although it was, and this, if it was a linear molecule, this dipole moment should have been, the net dipole moment should have been 0. But we find it has a net dipole moment, which explains that the reason for it must be that this molecule is angular, and being angular, there's a vector sum of these two dipole moments, which is giving it its resultant dipole moment. So we have the next molecule now, that is H2S. H2S is exactly the same structure again. It has a net dipole moment of 0.95. Now I'd ask you, why is the dipole moment of H2S less than that of water, although they seem to have the same structure? The reason here would be that sulfur is less electronegative than oxygen. Oxygen is more electronegative, charge separation is more. If the charge is more, the magnitude of the dipole moment obviously would be more. But H2S, on the basis of the value of dipole moment, you can tell also has an angular structure. So this was about molecules which are of AB2 type. Let us now move on to the next type of molecules of AB3 type. Wait for that video, tune into it when I come in next, and if you found this video useful, please give it a thumbs up, subscribe to my channel, recommend it to all your friends, recommend it to any student of chemistry that you know, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.